Hi, this is Dr. Staley. Today we're going to be doing the titrations in order to measure the amount of ethylenediamine that's present in our nickel complex salts. So here is the experimental setup that we have. There we go. We've got our burette that we're going to be using to actually add to actually do the titration itself. This is used to add a very well-known volume, by which I mean that you measure the volume after you add it. Here we've got our samples of Salt B, and here we've got our sodium hydroxide and our hydrochloric acid. There we go. Now, one of the things that you'll notice about the sodium hydroxide and the hydrochloric acid is that one of them actually has liquid in it while the other one does not. That's because carbon dioxide dissolves in water, and when it does so, it forms carbonic acid. Carbonic acid normally, then turns back into carbon dioxide and comes back out of the water, and so you have an equilibrium. Although that is not true if your solution happens to have a strong base in it. If it has a strong base, then the strong base reacts with the carbonic acid, and that turns it into carbonate, which stays in the water. And then more carbon dioxide dissolves, turns into carbonic acid, reacts with even more base, and so on and so forth. So you end up running out of base. That is, you end up running out of base if your solution is open to the air and more air is able to come in and replace the CO2 that gets used up in the reaction. And so that is the reason why I haven't actually filled this yet. If you have your strong base in a bottle and your bottle is well sealed, then the amount of CO2 that can actually get into this solution is whatever happens to be in the bottle in the first place. So by keeping your sodium hydroxide in a bottle and keeping it well sealed, you're basically making sure that its concentration doesn't change too terribly much from what it was when you first put it in there. Now, what we're going to be doing is we're going to be reacting so we're going to be using the hydrochloric acid to dissolve some of the salt, and in doing so, the hydrochloric acid is going to react with the ethylenediamine and is going to protonate it. We're going to end up with, so that's going to give us some concentration of hydrochloric acid that is lower than what we start with, and that is going to give us some concentration of protonated ethylenediamine. Here we have bromocresol green, which is a dye that changes colors, and I apologize, my description of the color change is going to be kind of wonky because I'm colorblind and so I have a hard time seeing these things. Anyway, this is going to change colors depending upon the relative concentrations of acid or base. If there's more strong acid present, it's going to be one color. If there's more strong base present, it's going to be another color. So basically, we're going to use a known set amount of this to dissolve this, and then whatever HCl that's left over, we're going to add this to it. It's going to cause it to be one color. Then we titrate in sodium hydroxide until we get a color change. Once we get that color change, we know that we have passed the point where all of the hydrochloric acid has reacted. And at that point, we have a slight excess, or if we do it sloppily, a large excess of sodium hydroxide present. And that really is what a titration is. So a titration is when you have a reaction going and you are gradually adding in one reactant more and more and more until you reach the end point of the reaction, and you try to cut it off right at that end point in order to find out how much of the other reactant you had. Of course, that requires an indicator. So, now you might be wondering, Dr. Staley, why in the holy hell do you have two of these? Well, the reason I have two of these is because I am going to follow the advice that is offered in the video that is on Canvas about how to do titrations. The video that's on Canvas makes an offhand comment about how it's wise to do a rough titration first before your main one, so that you know roughly how much to add. What that means basically is burn one of your samples. See, what that means basically is burn one of your samples. See, if you're doing a titration, there are kind of two extremes to go for. On one extreme, you can value time, and you just do the titration as quickly as you can, get to the end point as fast as you can, and in that case, you've got some data. But it's not very accurate, because chances are extremely good that you've overshot the endpoint. On the other hand, you could do a titration very, very carefully, adding just a little bit, adding just a little bit more, little bit, eventually going drop-wise. There, you get data that is very accurate, but it takes a long time. The compromise between the two is to do one of each. First, you do a quick and dirty titration, where you just get to the endpoint. You try to be somewhat careful, but not that careful. You just want to get there as fast as you can. So that way, you know roughly how much volume it takes. So when you do the second one, the careful one, you know that before it took this much volume. It took this much volume to titrate. So here you can go quickly from here to here, and then do the last bit very, very carefully. But of course, in order to do that, you need two samples that have roughly the same amount of analyte in each. And again, if you have a hard time reading any of the things that I've written down here and that are in the video, I'm going to send out a document with all the numbers, with all the raw data. So, there we go. Now, before we actually start on the titration itself, one of the things we need to do is make sure that the burette is cleaned. Now, this burette has already been cleaned. This burette has already been cleaned by our wonderful and amazing lab techs. Specifically Maria, who has been the one letting me in here each day that I need to do these videos. So what I'm going to do is I'm going to start rinsing it out with DI water. Like I said, this has already been cleaned, but it is always nice to clean it again. And also, it's important that everyone cleans their own glassware so that you know that your glassware is clean. Right, so first I'm going to start by rinsing it down with deionized water. And then later I'm going to want to charge it with some of the solution that I intend to use. That's because right now, after rinsing this down with deionized water, any water droplets that are on the inside of the burette, which is quite a lot, are DI water. They're not the solution that I intend to use. And so when I add the sodium hydroxide solution, what's actually going to be in here is lower concentration than what is in the bottle. And I don't want that. So the way that I avoid that is I make sure that the way that I avoid that is I make sure that I rinse the burette with sodium hydroxide solution at least 3 times to, get all of the pure water down there so that any droplets that are left are the same concentration as what I want to use. Now, one of the things that you'll notice here is that I have not let all of the water drain out. The meniscus is right there right now. I did that on purpose because I want to make sure that there are no bubbles in here. If there's a bubble, then it won't let the solution go down, and importantly, it also will not, um, and importantly, it also will make the measurement a lot less accurate. And in order to compensate for the fact that that is in fact DI water there, I'm going to do a 4th rinse instead of just the 3. Now, this is the container in which I have the sodium hydroxide solution, and it is closed. It's closed down here and it's closed up here. That way I don't have any air getting in. In order to get the solution at the bottom, I need to open up the top so that the volume that goes out the bottom is replaced by air coming through the top. And then for very obvious reasons, I want to close the top again immediately. So I make sure before I put anything in that the stopcock is closed. And start rinsing this down. I want to make sure that there's a reasonably large amount in there before I let it out the bottom. Now, one of the things to take note about that I'm doing differently from the way that it was done in the video on Canvas, one of the things to take note about there is that in Canvas, in order to rinse down the sides, the demonstrator added some base to the burette and then took the burette off the stand and started rolling it back and forth and tilting it back and forth in order to get the base to coat all of the walls. I find that an easier way to go about coating the walls when you're charging the burette is to use the fact that the funnel is slanted. So if you look there, the funnel is not perfectly flat at the bottom. It's cut at an angle there, so that any solution that comes out is going to preferably come out on this side and go that way. So that when you are rinsing down the sides, you can have the funnel up high, pour in some sodium hydroxide, and rotate the funnel and rinse down all the sides that way. Well, yeah. I say all the sides, it's just circular, so I know it's only one side. But you know what I mean. Make sure that all the inside gets coated that way. And so that way you can make sure that the whole thing gets coated and you don't have to turn it sideways and risk, among other things, getting base on your hands. Need to get some more sodium hydroxide. I believe that's 2. Then last one. Now, one of the things, so if you do end up with bubbles in here, one way to get rid of them, if you do end up with bubbles in the stopcock, near the stopcock, one way to get rid of it is to just open and close this very, very quickly. Another way to get rid of it, especially if the bubble is preventing any solution from going down, is you open the stopcock and you can flick it, just very, very gently. Please remember that this is all glass and it's being held up here, so this part moving back and forth, what might seem like a little amount, could be enough to break the thing altogether. So if you do need to flick it, just very, very gently. You don't want to move it too much. Sorry, the tip touched the side of the waste container, so I didn't want to. There we go. That's the last droplet. Yeah, don't want to risk contamination. So, this is nice and charged with sodium hydroxide. And we are going to start our first titration in just a little bit. But first, I need to go back to the oven. Right, now that that's done, let's get back to our titrations. So, here is our burette, and here is the sodium hydroxide that I got before. You can see I stretched some parafilm over it so that it does not have access to the open air. I've also put some parafilm on the top of the burette so that stuff inside the burette does not have access to the open air. I'm going to be moving this back. I'm going to be adding some roughly 0.2 molar hydrochloric acid. Now, I should point out that even though the instructions say that the sodium hydroxide is 0.1 molar and the hydrochloric acid is 0.2 molar, that's not exactly the case. To one significant figure, it is, but we have more than one significant figure. I'll be including the actual concentrations later on. So, here's our first sample of nickel salt B. Here's our waste container and our handy dandy volumetric pipette and pipette bulb. These pipette bulbs, the way that they work is that you squeeze them in order to get some air out, and then this little switch right here determines what happens with the air that is in that comes out down here or goes into down here. If you press this up, then it sucks in air from the bottom, which means that it sucks in air from the pipette. If you have it down, then it allows air to go out the bottom without doing anything to this, which allows air and therefore solution to go out of the pipette. And this little bulb right here just gives you a little puff of air to blow the last little bit of solution out the bottom if you need to do that. Now, this volumetric pipette has been cleaned also, but I'm just going to charge it with some hydrochloric acid solution just to be on the safe side. Make sure any droplets in there are the right concentration of HCl. Now I'll remind you here that this pipette is calibrated to be 2 sig figs past the decimal, 5.00 milliliters to deliver without blowing out the end. So we can do that, and I'm going to blow out the end right here because I want to get that out of the tip and into the waste container. But when I go to actually do the additions, do the additions that I care about measuring accurately, I'm not going to do that. So here we go. Get some more hydrochloric acid into here. Come on, you. There we go. And I'm going to do an addition. Now, I do not happen to have a 10 milliliter volumetric flask on hand at the moment, so I'm going to be doing all my additions with this 5 milliliter flask instead. And that means I need to do 2 of them, because I need 10 milliliters of hydrochloric acid to make sure that all of the ethylenediamine is dissolved. Well, is reacted. I mean, it dissolves in water, but I need it all to react. There. Let's blow it out into the waste container. Alright. Now for nickel salt B. We start out with it not quite dissolved, so I just need to make sure that it dissolves. There we go, whole thing is dissolved. So next up, I am going to add some of the bromo cresol green. The instructions say to add either 2 or 3 drops. Personally, I find that it's hard to see the color change, partly because I'm colorblind, but also partly because 2 or 3 drops gives a very faint color. So I need to add 10 drops in order to get something that's easy for me to see. Next up, I am going to move this here. Add that right there. I'm going to take the parafilm off the top and take this parafilm off of the beaker. Let's go ahead and add sodium hydroxide that we are going to use. Oh, not quite enough. Just need to go and get some more. Oh, as a side note here, now, whenever you're working with something like a burette, you want to make sure that you keep the level that you're reading below your eye level. That's when you're adding solution, you want to make sure that you keep the solution below your eye level. That way you can move your eyes up and down so that you can accurately see where the meniscus is. The meniscus is the bottom of the curve of water, because water likes to climb charged surfaces like glass. Normally what that would mean is that you would have this back in the same position that it was when I started. In my case, it's a little different because I'm a little taller than average, so it's okay for me to do the additions with it right here. However, I do need to start showing the actual meniscus and the actual readings. So there, you see how the water is curved right there? The bottom of that curve, the bottom of it, so that is where we do all of our readings from. And if you look at the actual markings here, you'll see that the numbers that are marked out are milliliters. And they're milliliters that go from 0 at the top and go up as you go down. That's because a burette is designed to measure an amount of liquid or solution that is added. So the way to read this is 0 milliliters were added, 1 milliliter was added, 2 milliliters were added, 3 milliliters, etc. And so as a result, the numbers are totally and completely accurate for solution added, assuming that the bottom of that meniscus starts out right at the 0 mark. You don't want to ever try to do that. The reason you don't want to ever try to do that is because it will drive you crazy. You'll be adding a little bit, taking a little bit away, and it'll just take a long time. It's not worth your time. What we do instead is we put a waste container underneath, and we let the solution run out until the meniscus is below the 0 mark, so we can actually add it. Now, one of the things to notice is that in the time that I spent doing the measurements for the waters of hydration experiment, enough solution has run out the bottom that I now have a bubble right here. I don't want that. So once again, one way to get rid of it is to open and close this quickly. There we go. Another way would be if the bubble was right here and I had a hard time getting it through, flicking it. And now with that amount, I'm just looking here, the meniscus is still above the 0. So there are no markings up there, which means that I don't know exactly how much I have, and therefore I don't know how much is added since then. So by adding out just a little bit, I can get it down below the 0. So instead of driving myself crazy and spending tons and tons of time trying to get it right exactly at the 0, I now have the meniscus below the 0. So now let's talk about how we actually measure these things. This would be read as 0 point. You notice that, notice that there are 9 smaller markings between the 0 and the 1. That's the same for each of these. Those markings are tenths of milliliters. And if you'll notice, if you look really, really close there, see where are the markings? There we go. If you look really, really close there, it's actually possible to estimate how far the meniscus is between those smaller markings. So we want to basically estimate the hundredths of milliliter mark. And the way that we make that easier is we take out the background by using a burette reader card. So the burette reader card does 2 things. First, it's got a solid background on it. This yellow part right here is what I'm talking about. It's got a solid background on it so that there's nothing in the back distracting you. But second, it's got this dark part right here. And so what happens is that the light gets diffracted. The light gets diffracted so that the meniscus becomes really dark. And here we can see that the meniscus is between the 0.5 and 0.6 mark. And I'm sorry, I have a hard time reading off the computer like that. So looking at it, it's about 0.52, I'd estimate. And so that's what I put down. Salt B, burette measurements. For, what is the mass of the sample that we're doing? 0.0498. 498 gram sample. We're starting out at 0.52 milliliters. And so, now that that is taken care of, Now that that is taken care of, we can start doing the titration into the Erlenmeyer flask with our actual sample. Now, when we do the titrations, I want to make sure that I have my left hand here on the stopcock to the valve so that I can move it back and forth easily. If the valve is here, then it's easier while I'm, paying attention to this, it's easier to accidentally, forget that this is this way and try and do it that way, and you just end up having more control if it's on this side. Now, the way we do that, the reason we do that is because most people are right-handed, and so, you want to make sure that you swirl it in a way that you'll want to make sure that you swirl it pretty consistently, and that's easier to do with your dominant hand. Left-handed people might want to go like this instead. I'm very sorry for all of you left-handed people out there, but the burettes are designed with right-handed people in mind, so you can read it while adding more easily if you do it left hand here, right hand here. Anyway, so first we're going to do the quick and dirty addition, just to get a ballpark value so that we can do the careful and accurate addition later. I'm going to swirl this. Oh, side note. Another way to do this is to have a magnetic stir bar in there and to stir it consistently while adding. That's probably a better way to go about it, but right now we're in Gen Chem, and so we're trying to do this in a way that is, how should I put this? In a way that'll always work, even if you don't have that extra equipment. So here we go. Adding just a little bit. Adding just a little bit. Faster, faster. Now, as I add more and more, it looks like the yellowish color is maybe going away. Oh, there we go. Yeah, so the yellowish color doesn't go away, it just changes to a different color that is less yellow. There we go. That's our final amount. So there's our final color. Now, once again, I have overshot the end point here. So this is beyond. What we would want is something that's this color, but is very, very light. So I'm going to go ahead and use the burette reader card to go and take a reading. And this is at 13.2827. I'm going to say 13.28. It's at 13.28 milliliters. So, here, let me show you. I need to get a camera that's more mobile if I'm going to keep doing this much longer. There we go. Meniscus hard to see, meniscus easy to see. Over here until it's, let's see, 13, 14. Okay, so that is the first titration. And what I'm going to do is I'm going to subtract the initial reading from the final reading so that I know how much I actually added. 8. This is going to be 12 points. 76 milliliters added. Oh, come on, you stupid microphone. Yeah, if my lapel mic was more reliable, I'd be using that instead. All right, there we go. So that's what we've got so far for Salt B for the first measurement. And what I'm going to assume is that since I overshot the mark the first time, I can't go quite to that amount. So what I want to do is I want to go close to that and then go very, very carefully afterwards. So I'm going to assume that it's okay to go within 70 or 80% as long as my second sample has about the same mass, and it does. So I'm going to just split the difference between the two and go 75%. And I'm just going to make this super easy on myself and say that I want to add 8 milliliters. So I'm going to just assume that I can zoom through 8 milliliters. Nope, I'm a moron. That's not 3/4, that's 2/3. 9 milliliters. Assume that I can add 9 milliliters next time. Add that quickly, and then I don't have much of a problem. Now, one of the things to note here is that because because the burette can measure out accurately all the way down to 50 milliliters added, there's far more than another 13 mils left in it, which means that I don't actually have to add any more sodium hydroxide. I can just figure out how much is 9 mils past what I already have. And because I'm at 13.28, that means that I want to go down to 22.28 for the quick and dirty 9 mils. But obviously before I do that, I need to actually dissolve the other solution. Now, it hasn't been too terribly long since I used this for my hydrochloric acid, and no one else is here to use it while I was sitting around, so I don't need to worry about recharging it with HCl this time. I can just go right back into the additions. Oops, got some bubbles. That's not good. Bubbles are volume that contributes to the reading without actually contributing to the experiment. Come on, you. Come on. do that. Unfortunately, I don't have quite 5 milliliters left in here. So that leads to a simple solution. I need to get some more HCl. Back in a sec. Okay, I got some more HCl. It was just in that cart over there, or that cart boy over there. So, here we go. Right there. There. Okay, so not quite dissolved. Let's dissolve it. There we go, that's a lot better. Just like that. So, just like before, I'm going to add enough drops to see. Starting color, have a white background, so that it's easier to see what it actually is. And let's lower this down. More. So 22.28 is what I'm going for now. That's 13.28 plus 9 mils. Just gonna go ahead and add that in real quickly. Alright, so right now it's at about 22.19. What I'm going to do from here is, instead of just adding it in slowly, I'm going to try to go drop-wise. Add about 1 drop every second or 1 drop every half second or so. A decent rule of thumb is that for pure water at 1 atmosphere pressure, there's about 20 drops for every milliliter. So it shouldn't take more than a few minutes to reach the end point at just 1 drop per second, but of course getting that rate is very difficult. Usually you end up trying for it and it goes a little faster. And here I'm, again, not looking at the level on the burette, I'm looking at my sample. Can you see the sample? Yes, you can see the sample. So it's hard to see on that camera, unfortunately, but where the sodium hydroxide hits the solution, shoot, think I've overshot it for just a little bit. Where the sodium hydroxide hits the solution, the sample starts changing color on that location, even if you're not past the end point. Ah, drat. I did overshoot it. So that was 26 point, I'm going to say 0.03 milliliters. So 13.28 minus 26.03, that is 12.75. There. So either I was extremely lucky with my first measurement, and I came really, really close to the exact, and I got a really, really accurate measurement, or my overeagerness on the second was caused me to do a sloppy job on the second measurement. Of course, the only way to know for sure is to do it yet again. So what I'm going to do is I'm going to put parafilm on here, and I'm going to try it a third time and go more slowly. So I've made my third sample. This one has 0.0495 grams of salt B. You'll notice that there's some droplets here, there, on the Erlenmeyer flask. What happened there was that some of the salt sample got stuck on the sides up here because of static electricity. So I rinsed it down with the hydrochloric acid, and then I used some DI water to rinse down the hydrochloric acid droplets. When you're doing titrations, what ends up happening is that because the sodium hydroxide reacts with the hydrochloric acid, it's moles of one to moles of the other, not necessarily molarity of one to molarity of the other. We use the volume of the hydrochloric acid added to figure out how many moles of hydrochloric acid we added in the first place. And as a result of that, diluting the starting solution a little bit with some deionized water is not a big problem. Now, so here we go. Shoot. All right, so for the first sample, we ended up with 12.76 milliliters to the end point, or, well, till we stopped. For the second sample, 12.75 milliliters. So now I'm doing the third sample, and we are once again starting where we left off with the other sample at 26.03 milliliters. And what we're going to do here is we're going to try once again adding 9 milliliters quickly and then going dropwise from there. And this time I am going to try to get as close to 1 drop per second as possible so that the last part go through quickly. First, though, a trusty, handy-dandy indicator. There's it. Let's set the white for the background. So you can see. There we go. So 9 milliliters down from 26 is 35. So I'm going to let it go all the way down to 35 milliliters. All right, so 35 milliliters. So now what I'm going to do is I'm going to turn this very, very slightly. So once again, I'll make the comment that where the drops land tends to change color and then get absorbed into the rest of the solution. When you're getting closer to the end point, that happens with individual drops rather than needing a larger stream to actually see a color change. Oh. There we go. Very faint color. Fainter than before. What we do is we just touch that against the side right there. Make sure that it's rinsed down into it. And we've got our ending color. Yeah, that's fainter than it was. So now let's take the burette reader, read out and amount. This is 38.79. 38.79 milliliters. Okay, so 38.79 minus 26.03 is 12.76. 12.76. All right, so the quick and dirty measurement was 12.76 milliliters. The first attempt at a careful measurement was 12.75. The second attempt was 12.76. So at this point, I'm going to just come right out and say that my first measurement, the quick and dirty one, the one that was supposed to be inaccurate and just ballpark, is probably, that's probably pretty accurate. But it's always good to do it one more time to have confirmation. All right, so I'll put that, so here's the ending data. Just, go 12.76, the other one 12.75 and 12.76. Now, mind you, this is, even though these are very reproducible in terms of the volumes, that does not necessarily mean that they have exactly the same percent ethylenediamine, because the masses are different. The masses are very similar, but they are still different. 0.498, 0.0498, 0.0509, and then that third one was 0.0495. And again, do the measurements based upon the last two. The first one might be the same, but the first one was intended to be only a ballpark estimate. All right, thank you. This concludes the measurement of ethylenediamine in complex salt that was made using procedure B.